So we have an aromatics question. We're looking at the formation of nitrobenzenes. And the first part of this question is how we make the NO2 plus ion. You'll notice within the question that they're talking about concentrated nitric and concentrated sulfuric acid. That's the condition you would also have to remember if this question were asked in a different way. When you put them together, the H2SO4 and the HNO3, the sulfuric acid is actually acting as the acid here, the nitric acid is acting as a base. So the H2SO4 donates a proton, leaving HSO4-. The HNO3 accepts it to make H2NO3+. But I'm breaking that down within the first equation here. You can do it as two equations, but the H2NO3+ breaks down into H2O and NO2+, and I've got my NO2 plus ion to use in the mechanism itself. So now let's take a look at the mechanism. As is normal on the videos that I'm going through on here, I'm not going to name the mechanism until the end because I think it's important to reason it out rather than try to remember it as a fact. But the mechanism itself, I've got my nitrobenzene, I'm going to turn it into dinitrobenzene, and my NO2 plus is going to go onto the third carbon. Now my curly arrow is going to go from the electron-rich the electron-rich delocalized ring, which is always going to be the case in this type of mechanism, and it's going to go to the electron-deficient NO2 plus. I've got 1 mark for doing that. Now, to get that mark, I've also got to have that curly arrow going through the right part of the benzene ring. It should be adjacent to the carbon that the NO2 plus is going to join onto. Now from there I get my intermediate structure. You can see that my delocalized ring is broken. I've got a positive charge because it's slightly now electron deficient. My NO2 plus has joined as an NO2 on the third carbon, and I'm now including the H on this structure because that's going to be important for the subsequent marks. But I'm now up to 2 marks for the mechanism. The third mark is to show that that H is going to go, we're losing it, and the electrons are going to move back in to complete the delocalized ring. In terms of the mechanism type, well, NO2 plus, the positive, the fact that it's electron deficient, is hopefully telling you that it's electrophilic. And then what are we actually doing? Well, we're replacing an H with an NO2. So it's a substitution, electrophilic, substitution, and we're done. So on here, we're moving on to chromatography. And we've got actually a relatively straightforward mark, but you've got to make sure you've got your ruler with you. Although on this one, actually, maybe you can reason it out without measuring it specifically. We'll take a look. The first thing that I'm going to do is have a look at the 2 distances that we would need to measure. We've got, for the RF value, the distance that the component has moved, and we've got the total distance of the solvent from. And from there, I could actually measure them out, do the division, but when I look at this, I've got A is 0.41, B is 0.46. That would mean that the spot was less than half the height of the solvent front, and it definitely isn't. I'd say it's significantly more than half the height of the solvent front. So I'm also going to dismiss C, 0.52. So I get my answer of 0.62. And you can do the measurements to confirm that, but I would be able to look at that, I think, and judge it quite effectively. Now, it's very easy to get tied up in knots on this question, stating in general terms what determines the distance travelled by a spot in TLC. And you are thinking about the fact that in one sense it's dissolved in the solvent, but it's also being held back by the paper. So we need to think of it in terms of their affinity for the mobile and the stationary phase. Now, what we mean by that If they have a greater affinity for the stationary phase, they will travel less far up the paper or up the TLC plate, and if their affinity for the mobile phase is greater, they will be carried further by the solvent. But this is what we're looking for as the answer for 8.4. For 8.5, to obtain the chromatogram, the TLC plate was held by the edges and placed in the solvent in the beaker in the fume cupboard. We then placed the lid on the beaker. One other practical requirement when placing the plate in the beaker. The most fundamental thing here is that the start line must be higher than the depth of the solvent. Why? Because if you put it in and your sample that you're testing is on a line that's below the depth of the solvent, it's just going to dissolve into the solvent rather than get carried up the paper. The paper is soaked through. On to 8.6, so quite a lot to read here. It's worth taking the time to do it. We've got a second TLC experiment using 1,2-dinitrobenzene and 1,4-dinitrobenzene. It's an identical plate. The RF value for 1,4-dinitrobenzene is greater than that of 1,2-dinitrobenzene. And we need to consider the relative polarities of the two and explain why 1,4-dinitrobenzene has the greater RF value. So for the relative polarities, 1,2-dinitrobenzene is more polar. Obviously, we need the explanation mark as well. The 1,4-dinitrobenzene is less polar, so it's less attracted to the polar stationary phase. Now that means that the 1,4-dinitrobenzene has got the greater RF value. And finally, on this question, we've got a third TLC experiment using 1,2-dinitrobenzene, an identical plate used to the one in 8.3, the same conditions, but the solvent here was a mixture of hexane and ethyl ethanoate. The student here stated that the RF value would be greater than that of 1,2-dinitrobenzene in the experiment in question 8.6. Is the student correct? Well, you need to say yes. You need to justify that. So we're not at marks yet. But if you say no, it's an automatic 0. It cannot be credited with any marks. But why is it yes? Well, the solvent is more polar, so we get a mark for stating that. And the polar isomer has a stronger affinity to the solvent or the mobile phase.